let me introduce Robin Deeley from Boulder, who is going to talk about a counterexample to the HK-conjecture that is principal.
Yeah, so I'm going to keep my mask on as long as everyone can hear me, but I'll take it off if I get to it or whatever. So I want to start by thanking the organizers for inviting me to speak and doing all the organization. What I'm going to talk about is all on the archive. I could write down the archive thing, but it has the same title as the talk, so you can always just Google that and find the paper if you're interested. And the talk will start out maybe a little heavy with the statement of this conjecture, and then it will lighten up significantly with some examples. So if this first board, you feel a little overwhelmed, don't worry, we'll get some explicit examples and things like that going soon enough. All right, so this conjecture is the following. So I'm going to start with just the statement. So the statement is as follows. So if G is, and there's a whole bunch of words here, second countable a tau, essentially principal, but we're going to mainly care about principal, so I'm just going to put that in brackets. Minimal, only one word, and ample, groupoid. Right, we like groupoids, yeah? All right, so this is what we hope to be true. So we have a whole list of words, which I'll explain a little bit in a moment. Then what's going to happen is the K-theory of the reduced C-star algebra of this groupoid should be isomorphic to another thing, the homology associated to this tau groupoid. So it'd be star times 2 groupoid here. So this is K-theory. This is groupoid homology, tau. Okay, so this is a little heavy, so if you don't know these definitions, I'm going to not talk too much about these definitions. What I want you to get out of this is that the object we're interested in is the K-theory of this C-star algebra. So this is the thing we want to know about. And what this is an in-principle computation of it, if this conjecture holds. So we want to think of the right-hand side here being something that is in principle computable from our groupoid, whereas the K-theory of this reduced C-star algebra is a little mysterious. And in the magic case, when this conjecture holds, they're the same. So we're good to go to sort of in principle just compute this, not even have to make the C-star algebra up, and just sort of call it a win on that. All right, so I do want to go through some of these words, and then we'll get to our sort of first examples and things like that. Right, so G is a groupoid. G0 is its unit space. And we have R and S, these maps, to the range and source maps from G to G0. So then a tau is R and S, our local homeomorphisms. Minimal is a statement about the orbits. So let's say it like this. R of the set gamma G, the groupoid with these equal to some unit in our unit space. This is dense. Dense for each U. G naught. And then we've got ample, which is G0. Let's just say this is the Cantor set. You can be a bit more general in this, but we'll just take it to be the Cantor set. So we have zero-dimensional, totally disconnected unit space. And then I missed one, yeah, principal. And principal is the statement that the map from G, this is one way to say it, you can say it a few different ways. So we have this map from an element here to the range in the source. And in principle, this doesn't have to have too many properties, but in the case of this is principal, this is injective. So what that's saying is if I take, you want to think of this being an equivalence relation groupoid, basically. Right? So what we're saying is I take two elements in the unit space, maybe there's no arrow between them, that's possible, but if there's one arrow, that's the most. Right? You can't have two different arrows going to this, between these two. All right, so good times. That's the heavy stuff. Now let's just start talking about examples and the groupoids that I like and how they come up and how the counterexample sort of comes up in sort of a natural way by considering these examples. Yeah.
Can I ask questions?
Oh, of course, yeah.
What does almost principal mean if this is principal?
Oh, essentially principal, you phrase this in terms of the unit space, and what you say is that the isotropy is, the interior of it is exactly the unit space. So it's sort of, the difference you want to think of is if I had a discrete group action acting on some space, it would be the difference between it being free and it being topologically free. So having, some fixed points, but, essentially not very many. So that's the difference between these two.
Thanks.
Yeah. So, in this talk, we're going to be dealing with principal. Maybe I should make a mention right now. I should get the date. So, the first counterexample. The HK-conjecture. It's by Scarparo. And this, I think this wasn't published until 2020, that's what I wrote down, but this was on the archive, 2 years ago, maybe 3 years ago. And it is essentially, no brackets, essentially principal. Right, so there was already this counterexample in the essentially principal case, and then a number of people have proved, theorems about the principal case, and there was at least some optimism, right, that maybe it would be true in the principal case, and then this counterexample is what I'm talking about today. All right, so I'm going to start with a very explicit example. So we want a cantor set, so let's call it maybe omega for a change, but this is just going to be sequences of zeros and ones, one-sided ones, and we're taking the product topology. This is a nice realization of the cantor set. And then I'm going to have phi be equal to the odometer action, which is otherwise known as add 1 with carryover. So I'm going to describe what this is. I think 50 to 75% of the room has seen this before, but that doesn't matter. If you haven't seen it, it's all good. So what this does is, if I have a 0, and then whatever, right? What do? I just add 1, and that's what I get. So I get 1, and then the same thing. And then if I had a 1, and then a 0, and then whatever, right? We can imagine what would happen in this scenario as well, right? I add 1 to 1, I get 2. 2 isn't in my collection, right? I'm doing sort of binary addition, so I should carry over, right? I should add these two together, and then add a 1 to the next coordinate over. Right? So we're going to get a 0, then we're going to get a 1, and now hopefully this pattern will work for any sequence where at least there's 1 0, right? If I have 10 1s in a row, I'm going to change them all to zeros, right, and then carry over to that 1 being 1. But there is one point that we haven't defined this for, so I want to think about what happens when we apply this map to the sequence of all 1s, which is a perfectly good sequence in our space, and we just do what we wish we could do in the car. This is the you have to make this joke kind of situation, right? And we just take this all the way back to all zeros. And right, this is a perfectly good map, at least. And this map has two important properties. So phi mapping the cantor set to the cantor set gives minimal and free action of the integers, right? The integer action is just the one obtained by iteration. This is a homeomorphism, so we're going both in the forward and the backward direction. And, it's called minimal, so we better hope that the groupoid we make out of it is minimal as well, or the word would not be used. And then, like I was sort of mentioning, free is exactly what we need to get this thing being principal rather than essentially principal. The other, of course, the unit space of the associated groupoid is going to be this Cantor set. And then what's the last thing we needed? We got ample, we got principal, got minimal. Oh, a tau, right, is going to come because we have a discrete group, the integers, right? So this is another piece of the puzzle as well. All right, so this is one of my favorite dynamical systems, let's say. And now we're going to try to generalize this a little bit. Maybe I should write down what I just said in words. So the groupoid you make out of this, this action, omega integers satisfies the assumptions in the HK-conjecture. I mean, this particular groupoid does better, right? I mean, this groupoid is not the counterexample. You know, the HK-conjecture holds for this groupoid. We're going to have to do a little bit more work to get our better counterexample. Is there a clock somewhere? I can always just use my phone. All right, cool. All right, so we're going to try and generalize this. So, a generalization. Exit. And of course, there's an obvious generalization, right? I could just change this set, right, and make it another Cantor set where it's got finitely many elements, and I do an odometer action in that way. That's sort of an obvious one. But the real deal generalization is going to take a little bit more as its inputs. So our input, this could be actually generalized even further, but this is what we're going to stick with. So we're going to have Y is a closed, flat manifold. Maybe let's say with the following exact sequence. So we have any flat manifold has this property. I'll give you some examples if you haven't seen this before, which I assume most people maybe have not seen. So the fundamental group of the flat manifold fits in this nice short exact sequence where this D, this is the dimension of what was connected, you know, as well. And F is a finite group. So a couple examples just to at least make you believe that I'm not making things up. Right, so the circle is a nice example of a flat manifold, right? And you know, what is this exact sequence in that case? Well, it's just the identity map, right? We just know that the dimension, you know, is 1, and we don't have any finite group showing up at all, right? So this is F equals a trivial group, and this generalizes. You just take, you know, the torus. It's a nice flat manifold, and it's exactly the case when F is the trivial group. So, you know, what are some other examples? The only other example I'm going to draw on the board is the Klein bottle. That's the Klein bottle. And in this case, F is the 2-element group here, right? And how we see this, using, well, maybe I'll just draw the cover, right? So this is the twofold cover of the Klein bottle by the torus, right? And it's exactly the induced map from this covering that's giving you this short exact sequence, right? That's why this finite group is the 2-element group, because this is a 2-to-1 covering map, right? So if you're not so familiar with flat manifolds, right, you just think about these particular examples. The circle, the Klein bottle, very explicit examples. But it's a whole, you know, it's one of those things where, you know, I've spent, you know, my whole life not really caring about flat manifolds, gotta say, right? Then all of a sudden, right, you find out that they're cool and that all this research has been done on flat manifolds, and you have a good time learning all of this, right? And that's sort of the point for me about making this counterexample, right? That it was cool to learn a bunch of flat manifold theory. All right, so that's part of the input, is this flat manifold. And the second piece, so, let's say we're over, fix a locally expansive, expansive self-cover of Y. Let's call that G, going from Y to Y. And again, let's, I'm being vague a little bit about what's this definition of locally expansive. I'm going to, draw 3 pictures. 2 will be locally expansive, 1 will not be, and we'll all, nod our head, and no one will, get up in a huff and leave the conference and never come back, right? So we'll all be happy. All right, so here's some examples. So, y equals S1, which just for the convenience of the formula, I'm going to think of being the unit circle inside of the complex numbers, right, this unit circle. And then G can just be given by the squaring map. And if you draw the picture of this, which I'll do because we got a little bit more room on the board, sort of see the local expansiveness. I like to draw this like this for reasons that will maybe remain mysterious. But this, top half of the circle, what happens to it under the squaring map, sort of gets expanded along and come to here, right, to cover the whole thing. And likewise with the bottom part, right? So hopefully this sort of feel of locally expansive is sort of a little bit clearer, right? I take a little line segment, not a big, if I take something too big, it's no good, right? And what happens under this map, it sort of gets pulled apart a little bit. So, nature of this expansiveness. Right, so, I should say locally expansive. Then we have y equal to the Klein model. And G, I'm just going to draw a picture. Picture like this, right? So I'm going to try and cover the Klein bottle by itself. I'm going to use 9 copies of the Klein bottle to do this, and this is what it looks like, right? So up we go, down we go, up we go, down we go, and then these ones are all over. Right, so got a little messy, but we've taken 9 copies of the Klein bottle, we've stuck them inside. Now what's the covering map? Covering map is, say for this one, I just expanded out to this whole thing, just like I expanded this piece to the whole circle. And then, say for this one, it's a little bit trickier, right? You've got to actually flip it over because of the way things are, but again, you're sort of expanding out in all these directions. So this is locally expansive, expanding. And then, let's say Y, Klein bottle. Let's call it H. It's not going to be, right, I could, do something where I just go, maybe I slice it like this. And here we go, like these. All right, so this is a perfectly good cover of this, but this is not locally. Right, it's sort of expanding in one direction, but not both, right? So we sort of want this to happen in both the coordinates if we're thinking about the Klein bottle or the torus. And you can come up with various other, covers that would not sort of be expansive in all the directions that we're seeing. Right, everyone's sort of clear with this picture. We're all happy with the sort of distinction between these. Okay. All right. Now you might be wondering, it's very natural, right? We want to get the Cantor set somewhere, right? There does not seem to be a Cantor set on the board anymore, right? It's only this flat manifold, so we've got to make a Cantor set out of this situation. That's what we're going to do. So consider the following. Right, so I look at G, and it induces a map from pi 1 of y to pi 1 of y. And because this is a covering map, it's an injection, right? And I know something else, right? These let's say self-cover, let's say, of degree n, right? It's of some finite degree because everything's compact, so this is all good. But it's this map, right, is this injection, and, you know, its image is sitting inside here as a subgroup. And that's what we're going to build our Cantor set out of. So we're going to take 1 of y over g star of y. And we're going to map 1 of y mod g squared. Doesn't matter how we write this. Y. So this is an inverse limit construction. So 1 of y over g cubed star of y. Where do we go? And so this is a space that we're making, and we want to think about what the structure of this space is, right? So y equals s1, g equals t1 z squared, right? So what do these mysterious things look like? Well, this looks like this. This looks like this. This looks like this. And we're going out like this, right? So we're taking, we don't really want to think of these being groups because there's no reason it's a normal subgroup and things like this, so we want to interpret this just being, you know, sets. In this case, they're groups because it's a normal subgroup and everything. But so this is the 2-element set, this is the 4-element set, this is the 8-element set, and we want to think how we're coding these so that this makes sense or, you know, connects with what we had previously talked about, right? I had this odometer on the board. It looked all very nice. So, you know, what should this set sort of look like? It should just look like a set of 2 elements, right? 0 and 1, that's it. Now, when I do the 4-element set, maybe I want to interpret this a little differently. I want to do it in binary so that I see this sort of relationship with what's going on in what we did before with our odometer in the sort of traditional sense. And then we would do, for this one, we would again, right, use binary. We'd be just adding another digit, right, to this binary expansion. And that's exactly what this sort of inverse limit is encoding, right? It's encoding sequences of 0s and 1s now. So this is exactly the same Cantor set. I mean, all Cantor sets are the same, but this is explicitly, right, realized in the exact same way as the space that we had in our original dynamical system that we're talking about, right? Our 0, 1 sequences, and now we wanted to have this action that was add 1 with carryover, right? That was the action that we had on the board. Right, so, you know, how is that going to act here? Well, what is add 1, right? It's just a group operation, right? Applied to the generator of the group, right? So the fundamental group of the flat manifold, in this case, the circle, actually acts on this space that we've produced, right? So let's just write that down. Let's call this something first. Call this omega. So y1 y, x1 omega via. So what do I have? I have a bunch of cosets, elements and cosets. And I have G wanting to act on this, right? So for G is an element in. And what should it do? Right, there's only one thing to do, right? We've got a lot of G's on the board, and we know we've got a group, right? So we just want G to act on every single coordinate. Right? And sort of the magic is that's exactly add 1 with carryover in this case where we've realized them back as these binary extensions. That's right. This gets called a generalized odometer for this reason. So this goes on. G naught. G1. G2. So, in fact, when S or Y equals S, 1, G equals the squaring map, then we get the odometer on 0, that example we started with. But now we have, a much richer class of these systems to consider, and we can attempt to understand what their K-theory and what their homology are. And what would we hope for? We would hope for a theorem that takes a system like this and says the K-theory is related to, the K-theory of the flat manifold. Ideally, it's not going to be the K-theory, it's going to be the K-homology, but who cares, right? And we would do the same thing, right, with the groupoid homology, right? We would hope that, for this system, its groupoid homology is actually explicitly related to the homology of that flat manifold. And then we have something to work with, right? If we know something about the K-homology and the homology of flat manifolds, we can start looking for a counterexample, play with what we have for this. All right, let's see if we're on track. Great. Okay, so here's the theorem. Yeah, if anyone has questions, go ahead. Feel like it. This is a moment to pause and achieve something. We know what systems we're dealing with. If everyone's okay, let's keep going. All right, we're good. Okay, maybe I should make one other statement about this before I go on. Right here, there was nothing special about this being this locally expansive. There was nothing special about it being flat. None of this is coming in. That will come in later, right? And in general, right, you can make one of these odometer actions not even out of a cover, right? All you have to do is say I've got a chain, nested chain of these finite, order subgroups, right, sitting inside there, and make the system out of this. So here's the theorem. Bureau. This is from the paper with the original counterexample. So we've got two statements about the K-theory and the K-homology of such systems. So G is odometer, generalized odometer. The reduced K-theory of G is isomorphic to following limit. This is now an inductive limit of the K-theory of the group C-star algebra of pi 1 of y. And then brackets, that's all right. And then there's some map, maybe we'll call this G K3. There's some sort of induced map. And then the homology of G is isomorphic to the limit of the homology of the group, pi 1, y. G homology, some map. So these are stationary inductive limits. Everyone's sort of vaguely familiar with this notion, right? We take a single group, we have a map between them, right? And we make this new group out of these things. And this is what I was sort of hinting at with this relationship between the K-theory and the homology being rooted in what's happening at the level of the manifold itself, right? And being able to compute it in terms of that. All right, so what do we take advantage of in our case? So in our case, our situation, y being flat implies a really nice thing. Y is a model for the classifying space, B. Right, so this classifying space, if you never heard it, it's fine, right? If you have, you know what it is. I'm not going to talk about it because it's only going to show up in this one result that we want. So what's going to happen is that's going to tell us a relationship between these two things and what's happening at the level of the manifold itself, Y. I should also maybe mention, let's say moreover, pi 1 of Y is torsion-free and satisfies the Baum-Kahn-conjecture. So these are the big hammers, right? And what it means for us is that we can reduce this to statements about y itself rather than the fundamental group. Implication plus that. Say it like this: K-theory of the reduced C-star algebra, pi 1 of y is isomorphic to K-homology of y and the homology of the groupoid. Oh, sorry, not the groupoid. Pi 1 of y is just isomorphic to the homology. All right, so those are, black boxes. If you don't know what the Baum-Kahn conjecture is, you've lived a happy life, for sure, right? But I got to learn it early on from my advisor, so, I know what it is. And, in this situation, it is explicitly telling us that there is this isomorphism. Right? That's what the statement says. It says there's an explicit map as well, right? But we only need, for our purposes, that we now have this statement that the homology and the K-theory that we're interested in are intimately related with the K-homology of y and the homology of y. Now, if K-homology sounds scary, right, that's fine. Don't worry about it. It's just like homology, but it's a generalized version of a homology theory. Similar to K-theory, but K-theory might be just as scary for you, depending on your situation, right? So you want to think, is there a conflict between these two statements, right? These are two different theories, right? And what we're looking for in our conjecture, if we go back and remember, is that there should be this precise relationship between these two things, right? In the case of our groupoids that we're interested in. And so that's where we're going to go with this. So let's maybe make a mark for finite CW complexes of dimension less than or equal to 3. We have, well, I should call this something for a finite CW complex. What are we calling our complexes? X, maybe? We have the K homology of X is isomorphic to the direct sum over I, over star, I of H I plus star. I don't want to write this. Yeah, let's just write it like that. Let's make this a little easier. H even of X, this is when star equals 0, and then H odd of X, and star equals 1. I sort of want to do this. I sort of want to do this even lower, right? Because we're in lower degree. Right? We know the dimension is 3, right? So all we're saying is the K theory. K0 is isomorphic to H0 and H2, right? There's no other groups up there, right? And the same thing with the odd. It's going to be H1 and H3. And what that's supposed to be suggestive of is that's sort of what we asked for in the HK conjecture, right? We asked for the even and odd homology of this groupoid to match up with the even and odd K theory of this groupoid, right? So as long as we have dimension less than or equal to 3, right, the conjecture, we don't know if it's true, right, but it seems plausible, right, because we're saying these groups are now going to be the same. Now, it does matter what these induced maps are as well, right, but it looks sort of suggestive that if it's possible this is true in that sort of situation. Now, if we're interested in a counterexample, what do? We want to say what happens when we have higher dimensional things, right? And so let's say this is definitely false. This is not true when the dimension is greater than or equal to 4. This again, we're dimension X. Right, so right there we see this conflict showing up between these two things. Of course, we're not home free yet, right? Because we have two issues to try and resolve. Right? Issue number 1 is I'm not allowed to take any finite CW complex in my machine. My machine relies on it being a flat manifold, which is a very particular type of thing, right? And then the second thing that's an issue, right, is what happens with these maps here, right? Maybe, you know, in these inductive limits, right, some part of the K-theory or homology gets killed, the part that actually sees the difference between these two theories, right? So there's these two things that need to be sort of resolved to get us where we want to go with this counter. That's the first page. All right. Any questions? Does everyone, you know, see these two things as the key to the approach? Right? That we first have to do something at this level, and then we have to do something at the level of these things.
So just in terms of the conjecture,
Yeah.
so we have the K-theory related to the direct sum of the homology. So if we have
Yeah, so that's how you would write the K-theory star really should be written as the direct sum of, you know, K0 and K1 together, and we're saying those pieces match up, right? It's sort of me switching my notation, which is bad form, but I was tempted to write, you know, H naught and H2, and then I got lazy and decided not to.
is this K-theory or K-homology?
This is K-homology, sorry, this is K-homology.
Okay.
Yeah, yeah. But the, yeah, this is K-theory, it's the C-star algebra, or it's up, down. Yeah, this is related to K-homology of Y through the Baum-Kahn conjecture, because of the Baum-Kahn conjecture stuff. But yeah, if I misspeak and say K-theory when I mean K-homology, you can yell at me. I'm okay with it.
Or just look at the stars, I guess?
Yeah, so I mean, it's one of those things, like I think, you know, in my younger days, I would have been confident enough to say, every time the star is going to be down, so you're going to know whether this is K-theory or K-homology, right? But then, you know, someone might ask a question, and I might start writing about the K-theory of, you know, I don't know, RP4, for example, right? If someone wants to see where this conflict maybe shows up in K-theory versus cohomology, and then I would be, you know, a liar. Who wants to be a liar, right? So, there you go. All right, so here we go with the details. All right, so here's theorem. I don't know if this is, yeah, we'll call it a theorem. All right, so for D greater than or equal to 9, there exists a flat manifold. I usually don't include the word closed and flat, but I always mean closed, connected, right? Riemannian flat, if anyone has other preferences of flatness. So this is a flat manifold Y with the dimension of Y equal to that D. Let's say such that. I'll explain this notation in a moment, so we're looking at the K-homology of Y. T is standing for the torsion subgroup, and this is standing for the order, the number of elements in that torsion subgroup. The number of elements in that torsion subgroup are strictly less than, I think this was my preferred notation for this direct sum business, to put them all together. So what we're saying is that the torsion in the homology of this flat manifold is strictly larger than the torsion subgroup of the K-homology. Everything's finitely generated, these groups, right? So these are finite groups, these torsion groups are finite, so it's no problem taking the order and all that sort of thing, right? And so this is, so the proof is involved, but the idea is fairly straightforward. So the idea is twofold. So one is the Atiyah-Hudson-Brook spectral sequence. So what that does is it gives you an explicit way of relating homology to K-homology, or K-theory to cohomology, right? It's a machine, the black box for the purposes of the top, right? And then the second thing is there's a class. So Y is something called a real Bott manifold. And again, I'm not going to go through all the details, but the idea here is these are a particularly accessible class of flat manifolds, where basically, to cut a long story short, is there's an input which is a matrix that contains zeros and ones, and that explicitly tells you, produces a manifold first of all, and it also produces, what its cohomology with coefficients in Z2 is, and various things like that, various invariants, like Stiffany-Whitney invariants and things can be just read off this matrix. So it's sort of a process where, what was Robin doing during the pandemic, at least for a month? He was just looking around at, what's cool about flat manifolds, and was coming across papers with various classes of them and trying to find one where I could apply the Atiyah-Hudson-Brooks special sequence to it because I had enough knowledge about that class's, homology and cohomology and various things like that. I mean, if people like the Atiyah-Hudson-Brooks spectral sequence, I'll say in one word what we do, or what I do, right, is I show there's one where D3 is non-zero. Right, that's the key to the whole process. Now, if you don't know what D3 is, neither did I 2 years ago, so it's all good, right? So that's that. That's not true. I didn't know what D3 was. I'm a liar already. Great. Okay. All right, so, let's just think about this in terms of where we're trying to get to, right? This is exactly step one in our process, right? It was, try and find a space Y, a flat manifold, where I see the conflict between these two things, right? And this is a precise statement about that kind of conflict that we're having. So now we have a real theorem that's not by me. So this is due to Epstein and Chu. And I did not write down the date, but this is in the 70s, for sure. And it's the following, right? For any flat manifold Y, there exists a locally expansive self-cover G, going from Y to Y, of degree, I think I called degree n previously, so we'll do that again, equal to the number of elements in the finite subgroup in the dimension of Y. Let's maybe put it in brackets here, I might have forgotten. Recall this F. This F was on the board previously, but let's recall what it is, right? This was exactly so that was from that exact sequence there. So what this is saying is, and this is where flatness comes in, right? It's saying that we have, for any flat manifold, we at least have one of these locally expansive self-covers, so we can at least make, apply the machine I propose to this situation. And we know more about that situation because we know that it has a certain degree. And, a nice example to, sanity check was, what did I write down for the Klein bottle? Right? We had the Klein bottle, we had a self-cover, and how many elements, what degree was that cover to be locally expansive? Well, it was, count them up, it was 3 times 3, it was 9, right? And what happens in this situation? Well, we have exactly 2 elements in this group, so we have 3, it's dimension 2, so we're squaring 3 and we're getting 9. So that's exactly an instance of this theorem being applied to, say, the Klein bottle. But of course, proving this theorem is much more involved than proving it for just the Klein bottle. It's a nice theorem. I have this theorem. Oh, maybe we'll this is more, it feels more like a proposition. But if X is in the torsion subgroup of the homology of Y, then we know then the order of X divides this F, the number of elements in this group. In particular, this. I get x back. So this is saying that the order of this divides this f. Now I apply this, I get a bunch of f's hitting it, giving us 0. There's only one left over, right? That's the one giving us just x. And what this, maybe this is a nice time to talk about why this is true for the Klein bottle again. Right, so you think about the Klein bottle, what's its homology, right? Its homology in degree 1 is the integer's direct sum Z2, right? And you think about how this, was 9, and how it's acting on that, and acting like the identity on that Z over 2Z part, right? And in general, this is coming from a map called a transfer map that's associated to a cover that gives you this sort of theorem. So this is, a version of this is in Hatcher's book on algebraic topology. This is the sort of classical thing about the transfer map. All right, now it's the moment. I have 5 more minutes, right? We changed from 45 to very quick. All right, so we have another lemma. G is as in this theorem over here. Theorem. Then we had that map of Gene homology. Right, so let's just remember what that was. We know that there's this connection between the homology of the groupoid and the homology of Y, and it's an it's an inductive limit of those pieces, right? The H star of Y. And this was the connecting map in each one as we go along. Right, so what this is, this restricted to the torsion subgroup of the star of Y is equal to the identity. So this is using the previous lemma and some knowledge about what this induced map is. So if you like covering space theory, I sort of hinted at it already. What happens is that this map is exactly the transfer map in this case. So again, we're taking advantage of the fact this is the transfer map, and then we know how that behaves. So, again, if you like maybe groups, two finite groups, you have a finite homeomorphism, right? And you get a transfer map at the level of homology. And this is analogous, at the level of covering spaces, you have the same sort of theorem. All right, so why is this all very good? Let's put it all together and give our counterexample. Is this? So now we take Y as in the first theorem. That's the one I just erased, right? We take Y with dimension 9, dimension 10, whatever we feel like at 11, 15, that has this property that we have this conflict between the torsions, with G as in, I'm just going to write star because I'm sort of running out of time. That's this one here, right? So we first fix our flat manifold of dimension 9, 10, whatever it is. Then we take our locally expansive self-cover from Epstein and Shub, and then we think about what's happening with the torsion of these things. Then we have that the torsion of the inductive limit of the K homology of Y with G K homology. Look at this one more. This order of this is less than or equal to the torsion in the K homology of Y. That's just a property of inductive limits that you can't create more torsion in these inductive limits if they're stationary. And then we know something about this. We know this is strictly less than the torsion in H star. It's 2I Y order. And then finally, this last piece, we know this actually equals the torsion that we have in the inductive limit associated to this, because it's actually like the identity at each stage, right? So the torsion group is not changing at all in that inductive limit process. So then this equals the order of the torsion. Oh, I should have a direct sum. Sorry about that. Direct sum over I. Oh, yep, of H equals 2I. Groupoid. Boom. And maybe I should have written one more thing here, right? This is equal to the torsion in the K theory of the reduced C-star algebra of our groupoid, right? Again, orders, right? So this is everything coming together, right? We wanted to see that these two groups are not isomorphic. And what have we shown? We've shown a little bit more. We've shown that the torsion in here is strictly bigger than the torsion in there. And in particular, that means that these groups are not going to be isomorphic. And that's the counterexample. All right, so I think that's it, but oh, right on time. We'll say that. I could say something else, but we're done. Good. There's the counterexample.
Does anybody have any questions for Robin?
Sure.
Are there any known cases where the HK-conjecture holds?
Oh yeah, yeah. So lots of them. So when Matui was coming up with this conjecture, he proved it for a bunch of groupoids associated to shift spaces, like shifts of finite type and things like that. It's known for some K-graphs for some K. I can't remember how high it goes. Maybe 2 graphs or something like that. Some graph type constructions. There's a paper by, because I can't remember all of their names, I'm going to say the one I know the best, Rufus Willett and 3 other authors, that proves the HK conjecture for sort of these ample groupoids that have, in a certain sense, have low dimension. So there's this is maybe the last thing I was going to say, so it's a nice question. But there's this notion of dimension called dynamic asymptotic dimension for Untitled groupoids. And it seems like this might be playing the role that dimension is playing for these finite CW complexes in the context of this theory as well. So there's some indication that that's what's going on.
Is that isomorphism in the HK conjecture always the same map? It's just not always an isomorphism, or?
So that's the sort of vague part about this conjecture. That it's not like Bon-Con when there's an explicit map that people are shooting to say is the isomorphism. So Rufus and these other people in their paper actually make a couple maps that map to, H0 related to K0, H1 related to K1, and those sort of things. And that's what allows them to sort of go lower in dimension, right? To sort of say there's not that much homology, so we can deal with these maps.
Any other questions? It's like the speaker again.